In this video, we're going to talk about coding up your first solution to CartPole v0. Specifically, we're going to look at two very simple and very fundamental search algorithms in almost any sort of optimization problem. Number one is random search. Random search is used in optimizing machine learning hyperparameters, finding optimal parameters for linear programming problems. And here what we do is to really randomly search for different policies to see which one works better. In hill climbing, we actually do something slightly more intellectual. What we do is we figure out where is the direction that we can go higher meaning achieve a better policy outcome, and we go to that for a small step. By repeating a small step that improves the policy, hopefully we can get to a very good policy at the end. Now, let us do some coding. Let's go to the code that comes with these videos, and if you go down to chapter 2, the folder for chapter 2, you can see that there are two algorithms that we can start implementing to kind of create a more intelligent strategy for our agents navigating the CartPole environment. The first one we're going to do is a random search. So let's click on randomsearch.py, and you see a partially implemented reinforcement learning solution. So let's walk through this very quickly. So from the top, I'm importing some libraries that we need, and then some logging set up. And then the first class that we have is a class called harness, which is kind of what you use in training. And the only thing that a harness does is it allows you to run an episode, provided that you have an environment as an agent. So very classic reinforcement learning setup. And this is actually not that much different from what we've implemented in the first few videos. Basically use the environment.step loop, getting the next action from the agents, and then tallying up the reward at the end. The second thing that we have is linear agents. So the idea behind a linear agent is very simple. The linear agent keeps a set of parameters, a set of four parameters, and that corresponds to what we've seen before, where in the CartPole environments, a new observation has four numbers, right? So the idea is we will have four parameters corresponding to the four numbers of each state, and then the parameters is going to multiply with the state to come up with the best action. So as you can see here in the next action function, I've implemented this for you already. So we multiply the parameters with the observations, and then if that is smaller than 0, we go left. If that is not smaller than 0, then we go right. So in a full-blown implementation of a proper policy, you would create some sort of training function that tunes the parameters so that given the observations, the parameters is going to guide the agents to do the right thing. But because we have to take it one step at a time, the first algorithm that we're going to implement is just random search. So the idea behind random search is very simple. You take the parameters that you use to make your decisions and literally randomize them every time you go through the environment, in hopes that one of the times you hit on a set of random numbers that gives you a policy to navigate the environment under question correctly. So now that seems very, in fact, it's entirely random, but for a constraint problem like CartPole is actually fairly okay. So let's jump in and implement this. So first thing we need to do is to create an environment. So gem.make CartPole v0. The next thing we need to do is to keep track of the best parameters, and then also keep track of the best reward we've been getting. Let's create a new agent that can have a set of 4 parameters for its policy or strategy, and we will also create a harness so that we can start training this agent. So let's train this agent for 1,000 times. And every time we run one episode of the CartPole as a reminder, that means that, until the pole falls down, we want to randomize the parameters, i.e. policy, in hopes of hitting a set of random numbers that make sense for the CartPole task. So let's do this here. Equals n and random, and we literally take 4 random numbers and then make them interval, and then we get the harness to run one episode with us, supplying it the environment and the agents. So what's happening here is we're feeding the harness the environment and the agent, and because we have randomized the parameters of the agents at the start of this step, it will successfully run in the episode with the new random policy and see how it does. And then obviously, its performance is aggregated in the reward variable. And then let's keep track of the best reward. So if the reward is larger than the current best reward, then the best reward is updated. And then we'll also save the best parameters. And the other thing is, in the CartPole task, if you survive 200 steps, that's considered pretty good. So at this stage, we'll just we'll just stop the training loop and say, we've found a set of parameters that gets us to 200 steps. And then, because we want to continually understand how the training is going, we'll also say, in the range of 1,000 steps, let's say, if for every 100 steps we print the reward so that we can keep track of how the agent is doing. So now we have the script ready. I've actually changed it to print out the reward every 5 steps because it actually doesn't take that many guesses to guess right. We can go back to our reinforcement learning course folder in our PowerShell and run the script that we've just done. So here we have Python chapter 2 in the random search. And so you can see that it has been acting the way we wanted it to, right? So every 5 steps it tells us what reward it's getting. So this time it survived 9 steps and nothing happened. But then shortly after that, before the 10th loop, we actually found a set of parameters that could let the CartPole survive to the 200th step. So then it print out the optimal policy in terms of the 4 numbers that, when multiplied with the state, gets it to 200 steps. So because we're doing a random search and every epoch we get different random numbers to try with the CartPole task, what you'll notice is if you run it multiple times, it actually takes different number of loops to get to the optimal policy. Not optimal policy, sorry. To get to the policy that gets it to 200 steps. So actually, that's a pretty interesting concept there. Getting the carts to survive 200 steps with the pole on top is one thing, so you successfully passed the test, so to say. But then that is far from the optimal policy. That's nowhere near the optimal policy. So actually, as the course goes on, I'm going to show you successively more rigorous searching strategies to find a policy that actually is optimal given the environment. So we have now seen random search, which is guessing a random policy every time and hoping that one policy brings you to 200 steps. Let's implement a more educated version. The search algorithm for a policy that brings us to 200 steps is called hill climbing. So hill climbing is a very simple idea, right? Much like you climbing a hill and you finding the step that brings you forward. In hill climbing, what happens is instead of jumping to a random policy every time in the training loop, we actually add a little bit of noise into the policy, i.e. we move the policy a little bit. And we see whether that policy results in a better reward in the current episode. If it does, we'll keep the policy and then we'll go again. So we'll keep the improved policy and then we again alter it a bit. If that results in an even better policy, then we keep that policy too, until we find the policy that gets us to 200 steps. Otherwise, we discard the move and we try a different move that is dictated by a small random change in the policy. So how does this look like? So in the same folder, open hillclimbing.py, and you can see that random search is implemented already. You can implement hill climbing in a very similar fashion. So again, environment is made. Now, we need a new parameter called noise scaling. What this means is how much does the noise or the random, how much do we move the existing policy, right? And again, we keep track of the reward, and we also have a reward parameter to keep track of the current reward. So then we have things, the agent, the hardness. So again, we go for 10,000 steps, and let's run the environment for one episode, harness.run episode, environment. So now in run, we have the current policy's performance, right? So let's see whether this performance is better than the best performance we have had, right? If it is, let's update the best performance. And then we update also, sorry, actually what it is we need to keep track of the O parameters so we can revert it. And then we need to find new parameters, so agent.parameters, and then we add a little bit of random noise, so noise and scaling times. There we go. So what this is doing is saving the O parameters of the agents and kind of altering the agent's parameters by a little bit, running one episode with the new parameters, and if the run is better than the last best record, we don't do anything, right? We don't do anything to the parameters. But if it doesn't, then we need to revert the parameters and search again. There. Again, if the reward is 200, we're done here. So let's give this a try. So what does this look like? Let's go back to a PowerShell and run, instead of the random search, hill climbing. So actually not very exciting. Randomly, it stumbled on something that gave it 200 steps in step 0. However, I have a more illustrative example. Let's try again. Sorry about that. So there we go. We have a more illustrative example of what sometimes happens in more complex environments. But this is actually great. So you can see we ran our hill climbing algorithm, and if you recall what happened before, you can see that actually we are stepping through many loops of the CartPole environments, and we've been keeping track of a policy that has been evolving through these steps. And you can see that, the record has been pushed continually until it gets to 200 points. And that is hill climbing. So that wraps up this section. We looked at actions, we looked at the environment, and we've coded up very simple solutions to find good strategies, including using random search and using hill climbing. So let's wrap this up. In this section, we explore the possible actions of your CartPole robot with the OpenAI Gym API, where you know how to think about what's the action space, and then you know how to explore left and right. We talked about understanding the environment of the CartPole. Specifically, we talked about key concepts in OpenAI Gym where there is a step loop, where you always step through new states or the next state of the environment with your agent. And OpenAI Gym always returns 4 different feedback variables so that you can use it to train a smarter and smarter agent. And at the very end, we coded up a first solution to CartPole V0. So in the next section, we're going to simplify things a little bit more so that we can explore the concept of finding the right policy in a bit more detail. So we're going to talk about a concept called multi-arm bandit.